Hey folks, let's talk about bond energies and how we can use bond energies to determine the reaction enthalpy. Now you may recall that energy and enthalpy are not exactly the same thing, but for these calculations here, they're close enough that we can go ahead and use bond energies to calculate reaction enthalpy. The basic idea is that chemical reactions involve the breaking and formation of bonds. And whenever we break a bond, we have to put energy into it. That should make sense. In order to rip atoms apart, you got to put some energy into it to do that. But the opposite happens. When we make a bond, energy is released during that process. So we can think about it this way. The way we're going to calculate the reaction enthalpy is we start with our reactants. And we're going to break all the bonds. And that requires putting energy into the system. And when we break all the bonds, we're just going to end up with atoms. We'll just have separated atoms if we're breaking all the bonds. And then we're going to make the bonds for our products. And let's just say here that our products are lower energy than our reactants. The way I've drawn it here, that need not be the case. But we're going to go ahead and make our bonds. And that involves a release of energy. All right, and the difference here would be our reaction enthalpy for this process. So to calculate the reaction enthalpy with bond energies, what we need to do is we need to look at all the bonds of the reactants, and we need to find the bond energies for all of those bonds. And then we need to look at all the bonds of the products and find the corresponding bond energies there. So let's take a look at this reaction that I have at the top of the page, which involves a molecule called ethene, sometimes also known as ethylene, reacting with hydrogen bromide to form something called bromoethane. So let's go ahead and do this. We're going to figure out the reaction enthalpy. So we'll start with our reactants. And we'll identify all of the bonds in our reactants because the total delta H is going to be adding up all of the bonds of the reactants and all the bond energies and subtracting from that all the bond energies of the products. Now remember, and then why are we subtracting? Because when the product bonds are formed, energy is released, so hence the minus sign. All right, so let's go ahead and do this. Let's figure out what we've got in our reactants. So let's list the bonds in our reactants here. All right, so we have a carbon-carbon double bond. All right, and we have carbon-hydrogen bonds. But you'll notice that we've got 4 of those, right? 1, 2, 3, 4. So we've got 4 carbon-hydrogen bonds. So we have to make sure that we include all of those. All right. And then we also have the hydrogen bromide, the hydrogen bromine bond here. For that. And actually I'm going to erase that and move it down a little bit here. So that's our reactants. Okay, now we look at our products. All right, so our products we're going to notice that I've got a carbon bromine bond, I've got a carbon-carbon bond, and I've got 5 carbon-hydrogen bonds. All right, so now I need to look up my bond energy. Now that I've determined all the bonds present, I'm going to look up my bond energies. So let's check this out. So we're going to go down here. I've got a table. All right. And we're just going to note that the carbon-carbon bond energy is, double bond, is 614 kilojoules per mole. So let's write that. The carbon-hydrogen bond energy is 413 kilojoules per mole. And again, we have 4 of those. And the hydrogen bromide bond energy is 363 kilojoules per mole. So if we add all those together, we're going to get the total bond energy for breaking all of the bonds of my reactants. Okay, so when we add these together, we get 2,629 kilojoules per mole. And again, that's the energy that's necessary to break all of the bonds of the reactants. All right, now let's look at our products. All right, we'll do the same thing. The carbon-bromine bond energy is 276 kilojoules per mole. The carbon-carbon bond energy is 347 kilojoules per mole. And the carbon-hydrogen we've already measured is 413, and we've got 5 of those bonds. Now there is a shortcut here that you could take, but I'm not going to mention that right now. I don't want to add to any confusion. So we're just going to take that 5 times 413. And now we can add these up. And we add these up, we get 2,688. Oops. Scroll back up. 2,688 kilojoules per mole. All right, so that would be the energy released. All right, so that's actually negative because that would be the energy released in the formation of the bonds in this molecule. So let's figure out the total now, because the total is going to be the reactant energies minus the product energies. Again, it's minus because it's released. Oops. And that's going to give us a negative 59 kilojoules per mole. So that's it. So for this one, we get delta H as being exothermic negative 59 kilojoules per mole for our result. And again, the idea is we just take the bond energies of the reactants and subtract from that the bond energies of the products, making sure that we count the number of bonds correctly. Reactants minus products gives us delta H for the reaction. So I hope that's clear. If you have any questions, make sure you ask.